Hello everyone, and welcome to Lecture 5 ME 296. This lecture covers the basics of breadboarding, some features of the ELVIS boards we're going to use in class, and then some of the measurement tools we're going to be using. So a breadboard is a prototyping device, and it allows us to see if the circuit does what we want it to without having to solder or tape anything together. Most common circuit devices have a model that is designed to fit into the breadboards, meaning that the spacings of the holes are standardized between each type of breadboard. A nice feature of mini boards is labeling of the rows and columns, which can be immensely helpful in keeping track of more complex circuits. I would highly suggest assigning row and column values to either end of a device such as a resistor before building a circuit, so you know where everything is going to need to go. This will simplify construction of a circuit and help it so you don't short anything accidentally. Now the edges on the either side are traditionally used for supplying power to the circuit and are labeled as such with plus and minus. And behind the scenes, it's pretty simple. Each row is connected across, separated by the divide in the center, and the power rails are connected all the way up and down vertically. So in practice, let's construct two different kinds of circuits. We have the red wires connected in parallel on our breadboard and the blue ones connected in series. So the top halves of the red wires are all on the same row, and the bottom halves are all on the same row, and we jump the divide with two additional wires connecting the same rows across. The blue wires are connected in series because the top half of each resistor terminates in the same row that the bottom half of the next resistor or wire begins. This connects them in series. We've also powered our breadboard via a battery down there at the bottom of the screen. And then we supply that power to our circuits that we've constructed via the yellow and blue wires across. Overall, using a breadboard is pretty simple, and it should be real easy to pick up. Just takes 1 or 2 days of practice. However, we aren't just using any breadboard, we're using the National Instruments ELVIS 2 Plus board. The overall setup is the same, it just has extra bits attached around the edges, which are really handy, and we're going to be using some of these bits throughout the semester. So the basic setup for what we're going to be using mostly is shown in these boxes here. The blue box contains the hookups for the digital multimeter as well as the oscilloscope. The purple and green squares on the left side of the big red box contain the power hookups, which for both the direct current and the function generator for the AC current. And the big red square is just two breadboards side by side. The gold squares show the LED hookups, which we're going to be using to show that our circuits are powered and that certain devices are working when we need to have them be working. And there are lots of other features, but these are the main ones we're going to be using. And to control these, the ELVIS board has a proprietary software suite, which it uses to collect data and control the features. This does mean that all of our input is going to be digital input, and that means that we need to keep in mind the limitations of digital input. Only discrete differences in value can be read, not continuous differences. And only frequencies below the Nyquist frequency can be read. And we're going to discuss the Nyquist frequency in another lecture when we start going over time domain features via Laplace and Fourier transforms. The software itself is fairly easy to use and is patterned off of the physical counterparts that you may have used before, especially the oscilloscope in 196. And if you need a refresher on what these devices do, I'll put some resources on the class Google Drive or a discussion post. All right, so just a quick note on measurement, just a refresher. There are two primary parameters we're going to be measuring, voltage and current. To measure voltage, we're going to use a voltmeter. And to get an accurate reading, the voltmeter needs to have the same voltage difference between the two voltmeter leads as the device we are measuring. And luckily, this is easy to accomplish because we only need to connect the voltmeter in parallel with the device that we're measuring. So you don't have to do anything extra, just touch the two leads to either side of where you're trying to measure. Unfortunately, measuring current is not as easy because you can't just connect in parallel, because that will just split the current and we're not going to get an accurate measurement of the current. So we're going to need to connect our ammeter in series, which means that we need to break our circuit and insert the ammeter in series and then reconnect it. Most of you should have some familiarity with how to do this, and we'll practice a little on our first lab, which should be coming up very soon. And then lastly, a final note about significant figures and our measurement devices. Our measurement devices only have so much precision. A physical DMM usually only has 4 available significant figures, so leading zeros have a huge impact on the precision of our readings. This is slightly mitigated by the digital multimeter that we're using for the software suite, which has a feature that automatically adjusts the values to be within an ideal range for what it thinks we're trying to do. But we're not always going to be trusting that because it's automatic, which means it thinks it knows what we're trying to do, but it's not always correct. So just keep the limitations of our tools in mind, and you're also going to be graded on significant figures, so be extra careful when using the digital software. All right, that's all for now. Thank you for watching.